logarithms have lots of unique properties. We're going to look at a few basic ones. If you go looking around online, you're going to find stuff about all kinds of different properties that we don't necessarily need right now. It's easy to get lost and confused. So we're just going to look at some basic ones. All right. So we know our connection here, our key relationship, that if b to the y equals x, that's the same as saying y is log base b of x. Okay, this y is the power of b that gives us x. All right, so keeping that key relationship in mind there, we can say what is log base b of b? Well, remember, this is asking a question. The question being asked here is, what is the power you put on b to get b? And the answer is 1, right? What is the power you put on b to make it b? Well, the power is 1, of course, right? Okay, so that means that if we have log, the base and the number we're taking the log of are the same, then the answer is 1. This is asking a question. What is the power we put on b to get 1? Well, if you take some base, any number, and you raise it to some power, we're going to get 1. What is the power you put on b to get 1? What is the power you put on a b to get 1? And the answer is 0. So the power we write on this b to get 1 is 0. So 0 is the exponent. All right? So with that in mind, let's think about some of these here, right? So this question here, what is the power of 123 we need to get 123? Well, because these are the same, this is 1. So using this property, we can see it's 1. You can also just ask the question, and you should be able to answer it there, okay? How about this one? What is the power we put on 19 to get 1? Well, the power you put on 19 to get 1 is 0. So the log of any base of 1 is 0. So the log of 1 is going to be 0. Okay? That's the idea. Okay? A couple more properties. So here we got a log, and it might be useful to put parentheses around it. Sometimes we put those parentheses, sometimes we don't. But sometimes it's useful to realize, this is inside the log, kind of in the same way when we say the square root of x squared, or x to the 30th, whatever. The x to the 30th is inside the square root. The same kind of way, b to the x is inside the logarithm. All right? So if it's helpful, put those parentheses. So what does this mean? What's the question? This is asking a question. The question it's asking is, what power of b gives us b to the x? All right? And it's kind of a question that answers itself, all right? B to what power gives us b to the x? That's what this is asking. Well, what does that question mark have to be if you want it to look identical to this? Well, that question mark has to be x. All right? So b to the x equals b to the x, right? So what is the power you put on b to get b to the x? It's x. All right? So in other words, looking at this example here, what is the power we put on 7 to get 7 to the 5th? Or what power of 7 gives us 7 to the 5th? Well, the power is 5. So in other words, these kind of undo each other. Okay, we're seeing here that a logarithm is the opposite of an exponent or a power. It undoes the power and gives us the exponent. All right. Now this one's a little trickier, all right? But this is another inverse operation, all right? Let's think about what this means. So first we've got to think about what this exponent means here. So what does that mean? What is log base b of x? Well, this is the number. This is the power that you can put on b to get x. So this is a number. It's a mystery number. And it represents the power that you put on b to get x. All right. Well, let's take that mystery number and let's put it on b. Well, what do you get? You get x. All right. So let's put that into some numbers here. Okay. So here we have 8 to the log base 8 of 9. Well, let's make sure we understand what this is. Log base 8 of 9. So this is the power that you can put on 8 to get 9. So this represents a number. This number exists. I'm not exactly sure what it is. X to the question mark equals 9, all right? So that's what this is. I would say that this number is about, I don't know, 1 point, a little bit bigger than 1, maybe 1.1, making a total guess, all right? So it's something like that. So this number has one purpose in its life. It exists for one purpose. This is the magic number that when I put it on 8, I get 9. Got that? All right. Well, let's take that magic number and let's put it on 8. Well, once you put it on 8, it performs its sole purpose in life. And its sole purpose is when you put it on 8, it transforms 8 into 9. All right? So, again, the big idea is that this, when you put a log base 8 into a power as an 8, well, you get that number back out. They kind of cancel each other out. Okay? All right. So those are 4 log properties that will show up and we'll be using, all right? So we have a couple of special kind of logarithms. And the first one is called a common logarithm, all right? We count in base 10. And the reason is right in front of you at your fingertips. The reason why we count in base 10 is because we have 10 fingers, all right? So good for counting. And so we have a base 10 number system, all right? So base 10 logarithms are very common. They're very useful, all right? By the way, what a base 10 number system means is that every digit in a number represents a number that goes up to 10, right? We only have 10 digits. We have 0 through 9. So the only numbers you can put in here are, there's 10 options, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. All right, so base 10 is very common. So log base 10 of x is commonly written as log of x. So it's so common, sometimes we don't write a number down here, all right? So when we see a logarithm written without a base, that means it's base 10. So here, this is base 10. The question is, we want to compute this without calculators, all right? For at least A and B here. Well, what does this mean? This is asking a question. The question is, what is the power we put on 10 to get 100,000, all right? So if you want to rewrite it, you can. So the 10 to some power is 100,000. What is that power? Well, x is 5. 10 to the 5th power is 100,000. What is the power we put on x, or on 10, sorry, to get 1/100th? Well, 10 to x is 1/100th. Well, we know that it needs to be negative to drop it down below. So x is negative 2, because 10 to the 2nd power is 100. All right. Well, what about log of 3/7? Oh boy. These were easy because they were just powers of 10, right? Well, we don't know this power of 10, so we need our calculator, all right? So we're going to go to our calculator here. So you can use Desmos, or you can use your scientific calculator, all right? And so let's pull this out. So on Desmos here, if we go to function, same thing on the graphing. If you have the Desmos graphing calculator or the Desmos scientific calculator, both are available under desmos.com. So on the scientific, if we go to function, we have a log key. On your graphing calculator, you'll have a key that looks just like that also. And we can do the log of 3 divided by 7. So in your graphing calculator, you'll have two keys that we're going to be using here a lot. One is log and one is ln. The one that says log is a common log. It's base 10. All right, so base 10 here, log of 3/7 gives us a negative 0.367. Okay, because this is asking what is the power you put on 10 to get 3/7. Well, it's negative because it's made it less than 1. Oops, negative 0.368. And this is an irrational number. Kind of like a square root of 2 is an irrational number. Well, what about the common log of negative 5? Let's find the common log of 5. So log of negative 5. And what happens? Uh-oh, we get a problem. This is undefined. This does not exist because you cannot take the log of a negative number. Only positive numbers can go in logs. And that's going to be important as we look at logarithms as a function in the next coming section. But before we talk about log functions, let's look at some equations here. And the key to solving a logarithmic equation is to convert it to an exponential equation and then solve it. All right, so here we have a logarithmic equation with an x inside the logarithm. So the key to any equation, not just a logarithmic equation, but any equation, is to change the form of the equation to make it look like something we're familiar with. And we're kind of familiar with exponents, but we're not super familiar with logarithms. We can't deal with this x that's hiding inside the logarithm. So we go back to our key relationship, and that is this, b to the y equals x, and that's the same as saying log base b of x is y. Okay, and we can go back and forth. So we've been using this here. All right, so if we have a logarithm, we can change it to an exponential, and if we have an exponential, we can change it to a log, all by swinging that base around. So we're going to swing that base around, and we get x plus 1 equals 3 to the 4th. Now, a little side note, if you go YouTubing it and look around, you're going to see a whole bunch of different ways to solve this using some fancy properties. You don't need to get into all that. You can if you want, but it gets a little complicated. So all we need to do is rewrite it as an exponential. So that 3 is the base. So we're saying 4 is the power on 3. So 3 to the 4th equals x plus 1. And 3 to the 4th is 81. And so x plus 1 equals 81. Subtract 1 from both sides, and x is 80. Okay, and there you have it. Now we do have to check. We've got to check that this works, and mainly when we check, what we're checking to see is that when we put this number in, that we have a positive number on the inside. So that's when we'll run into problems, okay? So yes, when you plug in 80, that's obviously positive, and you can check that is log base 3 of 80 equal to 4, and it is. 3 to the 4th is, 80 plus 1, I should say. 80 plus 1. That does check out. All right. Well, what about this? Uh-oh, there's no base. Or is there? What's that invisible number that should be there? It's a 10, right? So we swing that 10 around. 3x plus 10 is 10 to the 2nd. And so that's 10 to the 2nd we know is 100. And 3x equals 90. And x equals 30. Okay? That's the key there. All right? All right. So next we'll look at logarithmic functions, but that's how we can solve log equations.